Right, guys. What I want to continue to discussing, I want to discuss the function which is closely related to exponential functions. So I'm going to write here something like exponential stroke logarithmic functions. The reason why I'm writing it like that, I don't want you to ever think about an exponential function and overlook the existence of a logarithmic function. Because those functions, they are closely related to each other. It's like you're going to a five-rand coin. It has got a head and a tail. You can't just say I've got the head of the five-rand coin, the tail I have left to the dog. It's not possible. Then you don't have a coin. Altogether. So now let's look at this. There is our axis. So this is our x-axis. This is our y-axis. There is our mirror line. Okay. So guys, imagine that that line passes through the origin, isn't it? Is that right? Maybe let me do this. Good. There's the line. Our mirror line is always going to be the identity function y is equal to x, isn't it? I'm saying mirror line. What did we say about the function and the graph of the function and the graph of its inverse? What did we say? If we're looking at the graph of a function and that of its inverse, we say there's a special relationship there. What did we say there? The distance between the two graphs is equal to what? I think you know what you want to say, but you're not saying it the right way. Maybe it's the problem with English. It's not a problem. It's not a problem. If it's in English, it's not a problem. What is he trying to say? Somebody can say it in a more clear way. What is he trying to say? Yes. From the line y. Yeah. He's trying to say, basically, you can say it in the easiest way. The graph of the inverse is the mirror of the graph of the function across the mirror line, which is equal to y is equal to x. Now, what I'm going to do now, I'm really going to exploit that very well to actually introduce the logarithmic function. I'm going to exploit that. So what I'm going to do now, I'm going to put my exponential function here, which I take there, it cuts through 1 and goes through there. This is my y equals to a to the power x. I don't really mind what is a, whether it's half, whether it's 5, but I know all of them are going to pass through 1. That is 1 then. Agreed, isn't it? Then immediately we go to the fact which the guy is trying to say, that when you've got a function and the graph of a function and that of its inverse, one is a mirror image of the other across the mirror line y is equal to x. And the mirror line y is equal to x is what we call our identity function. Altogether. So that's the graph of our identity function. So which means if I made 1 here, that is a point on the graph of the function, I must just call mirror-wise and say the distance there to the distance there is the same. And this number which was here must be exactly the number which is there. And that is should be 1 as a mirror image of that number. So what am I saying? We can say that same thing in another way. What am I saying about the graph of this function I'm searching for? It passes through It passes through x is equal to 1. It has a 0 at x is equal to 1, because the value of the function there, y will be 0, x will be 1, isn't it? So now, if I come here at the origin, I can draw again a line there, go exactly that, and they go there, and they stop there. What can I say about that point? As long as the distance there are equal, what can I say about that point? The point is on the graph, isn't it? Because it's got to be symmetric there. If I come to this point, I would go mirror-wise there, go across the line, somewhere there, I've got a point on the graph. Are we together, guys? This is, I'm doing this thing graphically. I'm very sure that someone else somewhere in Honolulu or in Hong Kong is going to do it differently. But he do it differently according to his students. I will understand his students. But I think my student can follow what I'm trying to do there. All together. My most important thing is to come up with the graph of the function which is inverse to the exponential function y is equal to a to the power x. Are we all clear of what we're looking for? Okay. So once I've done a similar thing with a number of points, what am I going to do? Let me get some red ink there and draw this graph. I'm sure that this graph is going to come through here. As I draw it, I make sure that I imagine it equal distance from the mirror line, and then I continue this way. I can see it getting closer and closer to y. There it was getting closer to x. Because y here is the mirror image of x there, isn't it? So I've got those two functions there. My friend, maybe I haven't said what is a logarithmic function, but what I've delivered here is a function, a graph of function, which I can comfortably call y is equal to log base a. Remember, a was the base there, isn't it? A would be the base of the corresponding logarithm function of what? Of x. My friend, if you go to any book which is talking about exponential functions and logarithm function and does not have that picture, throw the book away. Are we together? I'm saying that with conviction, because please, when you're doing something, please believe in what you are doing and do it with conviction. Convince the people you are dealing with that this thing is supposed to be like that. This is supposed to be like that. That we call logarithm function. Yes, my friend. But remember, we said the other day when we were doing inverse functions, you haven't gone through the lectures again. We said our graphs would plot them on y, on xy coordinates. So even if we change the subject formula to get the inverse, we will always write finally the function as y equals 2. Otherwise, you cannot plot it on this graph. Are we together, my friend? Yeah. The most important thing now is there are two functions. Both of the functions are acting on x. Exponential function is a exponential function of x. A logarithm function is a logarithm function of x. Then on the graph of the function, there, you're always going to have x, comma, f of x. In this case, this function will be the function log base a. But if you go there, we're also going to have x, comma, f of x. But this function will be the x4 function. Am I making myself clear? I'm supposed to. Am I making myself clear? Okay, good. Are you comfortable with that? Right. Now, I want to go further now and talk about what does this really function, logarithm function, do? And experience all those things that exponential function will take x in that direction. and get y. And the logarithm function will take that y back into x, meaning they're actually inverses. All together. Okay. So, can I proceed? Can I proceed? Okay. Let me try to do these things which can be confusing sometimes. Okay. Now, let's look at this. Let's look at this. Just take two, the easiest example, just to illustrate the fact we're talking about, isn't it? So, let me call this making sense of the works of expo and log base A. I will just write here, maybe somebody never wrote this thing this way. I write expo base A, log base A. Isn't it? Those are just names of functions, isn't it? Okay. Now, let's take a number like 2. A number like 2. And let's say 2 to the power 3. We know that this will give us what? 8. And we'll call this exponentiation or whatever you want to call it. But I think you can call this thing exponentiation. Isn't it? Now, the logarithm function is the function which is going to ask us that given x as a result of exponentiation, what was the exponent? Now it is given this as a result of exponentiation, it's asking us what is the exponent. All together? Okay. Now, what I'm trying to say now is saying, if we know the base, like we know the base is 2, isn't it? We're saying 2 to the power x is equals to 8. Then we say this 8 is 2 to the power of 3. If you don't know how to get that power of 3, this is what you do. You put 8 here, that is a cross. You put 8 here, you divide by 2, you get 4. You put another cross, you divide by 2, you get 2. You put another cross, you divide by 2, you get 1. Then you are done. Isn't it? So 8 is actually 1 times 2 times 2 times 2. But in terms of 2, it's just 2 to the power 1, 2, 3 vectors. Isn't it? Okay. So these 3 here is talking about vectors. Isn't it? So now, then you can now say x is equals to 3, comparing there. Isn't it? Okay. This, what we're doing actually here, I can now call this thing, 3, is actual equal to the logarithm of 8 base 2. That's what I call the logarithm. Now the thing which calls the exponent, the power, is actually the log for the number you get to. So what am I trying to say here? Look at what I've written here. I want you to compare this. 2 to the power 3 is equals to 8, and compare it with, in other language, as log base 2 of 8 is equals to 3. I'm telling you that on both sides of the equation, I'm saying exactly the same thing. But I changed the language. What am I talking here? I'm talking here in the logarithmic language. Logarithmic language. Here, I'm talking in the Now, here I'm talking in exponential language. Are we together, guys? So now, let's move away from 8 and go to any number and any base A. Just saying, let's move away from 8, 2, and 3 and just move to a general kind of context, isn't it? So maybe let me do this. Let's move away from 2 and right. Right. What we had there, we can't lose our example. Let's look at our example. Have our example close, isn't it? What we had with 2, it was 2 to the power 3 equals to 8 on one hand. On the other hand, we have what? Log base A, base 2, sorry. Base 2 of what? Of 8 equals to 3. What I didn't say maybe before, look that every number we've got there is there, isn't it? Altogether. The only thing which is confusing here, there's this word log here. But I think this I could have written as x for 2, the function of x equals to 8. Altogether. Then somebody asks the question, why then write it this way? We choose what is more convenient and is more portable, isn't it? Altogether. This side we have no choice. we have no choice. We've got to use the word log. Etc. But here we've got a choice. We can write it that way. Altogether. But you must understand that just a function. That's a name of a function. What is important is to know what it does. So now, moving away from that and getting to any general numbers, we would say, if we've got a base A, we remember that A, we said an A is a number greater than 0, less than 1, and a number greater than 1, isn't it? We're not taking negative numbers there. So we're saying A to the power of X is equal to a number M. This means exactly the same thing as log. You can tell me what to write. Log base A of M equals to X. So guys, when you are now like solving equations, you might get an equation in exponential language. You might, if necessary, you might need to change it to what? To an exponential language. All together? Okay. So just I want to do this. This is very important for me and for you, or let's say for us. You must have that. Okay. Now I want to go back to that issue of that this function will take x that side and logarithm will take it back, isn't it? But we've already seen what happens there with this one. 3 is the argument, is the argument of the function. It gives us 8. Then when we've got 8, want to go exactly the same root of base 2, we call logarithm, we get that. What does that say? That is saying that the exponential function is the inverse of the logarithm function, isn't it? So what we can actually do there, this is what we can do. If we've got A to log base A of M. What have we done there? We've applied log and cascade with the exponential. This will be the same as log base A of M, sorry, of A, what am I trying to do there? Log base A I hope I'm right there. Which one? Let me write it correct. Maybe I made a mistake. Let's just write it correct there. Let's say we've got. Let me actually erase this thing because I think I made a mistake somewhere there. Let's just check. Let's just check that. Let's keep this. Sorry. Let's say now we've got two functions here. Let's maybe write it right there. Take this. We've got y is equal to a to the power of x, right? And then we've got y is equals to what? Log what? Log base a of x. Isn't it? Now I want to compose these two functions. Isn't it? What I'm going to do? I'm going to say log a of a power x. What's that? If they are inverses, I must get here what? X. What did I start with here? I started with an exponential, then I followed the log, isn't it? Then on the other side, I can say, starting with a log, then I've got log base a, sorry, not base a, not log of a, log base a of x. That is what you have done. Then you take that a to the exponent of that, you get x. Let's go slowly. You operate x, you operate this exponential, isn't it? Then you follow log, you will definitely get x. That's what we did there. We took 2, we elevated to 3, we got 8. Then we applied log base 2, we got what? 3. Is that correct? Let's start the reverse way now. We start with a base 2. Isn't it? We've got that number there. What's that number? Let's not talk about this number. But let's say now is the log of x base a. Then we do that. We must get back to x. If we start with a number, we calculate its log. We take x, you calculate the log of 8. What is that going to be? It's going to be the log of 8 base 2. It's going to be what? 8 base 2. 3. Yeah. Then you take 2, you exponentiate. This is 2, isn't it? You exponentiate with that log. What are you going to get? 8. So if you start from 8, you calculate log, you follow exponential, you go back to 8. But if you start from the exponent 2 with 3, you go exponential, you go back to the same thing. Now that's the identity, isn't it? So that thing there is very, very important to understand. I know maybe it might be confusing how you write, but this is actually I'm here, I'm just saying, I pick a number, I apply the log to a person base. Then I take the same base, I elevate to that log, I'll get exactly the same number. This is what's happening here. No. Listen to me. That's not how we write inverse. What you must understand is, this is inverse of export. All together. This is inverse of log base A. Remember we said that relationship is reciprocal. This one is inverse of that, then that is inverse of this. Is that right? It's like cousin. You are my cousin. Point to me. Say the same thing. You are my cousin. You are my cousin. That's the kind of relationship.
So now, what you told me at the point is going to be exponential
I don't know, but I'm sure whether I understand you, but I don't understand. Yeah. You always take the log and make an exponent of the base, the same base. You get the same thing. Don't you see it here? Look at it here. What is 8? Look at this. Let's look at 8. Let's look at 8. Let's just look at 8 here. What is 8? Let's say we have here log base 2 of 8. But what is 8? Log base 2. 8 is 2 to the power 3. Yes or no? Is that right? Now, what's going to happen now? If we take this thing reverse way now, we'll be doing the exponentiation, isn't it? We take what is the answer to this? It's 3, isn't it? It's 3, isn't it? If we do the reverse way now, where do we start now? We start let's take 2. What is 3 there? 2, 3 there is log of what? Base 2 of what? Of 8. Just check, compare the two things and see where you arrive. Altogether. Yeah. So in one case, what should you understand that the order in which you apply the function, even if you change it, their inverses, you go back to the identity. That's what I'm trying to do here. At this line here. Where is that thing? Here. I apply the exponential, I apply the log, I get x. I apply log on x, then that apply the exponential, I get x. Right. I think the best thing now, let's try to get an example of trying to work with something like this, then we can make sense what happens. How much time is there for? 9 minutes? 13. 9. Let's see. Let me just say, clear this. Now, this is what I'm trying to say now here. If we let's say we've got 3 to the power x equals 27. But I think I should have started somewhere first before I get here. I should have started somewhere else before I get here, especially the properties of logarithm functions. I think, let me do that first just briefly. Maybe we'll continue from the next lecture. The log of a base, log of a base a. What is that? Is equal to 1. But please understand that when you are saying log of a number, you are actually looking at the exponent to which you are going to elevate a in order to get a. A number which you are going to elevate a in order to get a. That means a to the power this 1 is going to give us what? 1. Isn't it? Sorry. A to the power 1, this 1 is going to give us what? A. So the logarithm is actually asking for the exponent to which you elevate this given base to get the number. In this case, is 1. Isn't it? Okay. That is important. So now, the other thing is logarithm of 1. You can also write that down. Logarithm of 1. What are we talking about here? 1 the number to which you're going to elevate this a to get 1. So a, want a number which you must fill here, but the answer must be 1. What's that number? So the logarithm of 1 was that 0. Altogether. Then now we also have got, if I've got n being equals to a to the power x, and I've got m being equals to a to the power y. What is the logarithm of n base a? What is the logarithm of n base a? Of n base a? Sorry? X is equal to log of n base a of n, sorry, of n, let me just say 2 and 2 and 2. It's like the value of n base a. And the y, logarithm of a of m. Do you agree there? Okay. Now, I want to answer this one. What is logarithm base a of n times m? I'm talking, in this case, I'm talking about n times m, which is equal to a to the power of x multiplied by a to the power of y, which we all know is equal to a to the power x plus y, isn't it? So what is the logarithm of m times n? It's x plus y. I said what is the logarithm of m times n? It's x plus y, isn't it? Then what does that mean? It means that this is the logarithm base that a plus logarithm of m base a. All together. So what do we mean there? We mean that the logarithm of the product is the sum of the logs. The logarithm of the product is the sum of the logs. Then you can easily proceed to division. If you take n divided by m, then you've got what there? What you've got there? You've got a x over a y. We know this reduces to what? X minus y. Then when you come and say, what is the logarithm of the quotient n over m? I'm now going to ignore a, because that happens with all places, isn't it? Let's just say log 7. So then what's going to happen here? This is going to be x minus y. But x is logarithm of n. Y is logarithm of m. That's another property there. So what you need to do now, you need to go through this and summarize, and those are the properties of logarithm. We're going to look at them later, solving other problems. Maybe we're too late here. 3 minutes to go. Let's talk. Right, guys.